Yeah, it's okay.
So thanks a lot for the introduction, and thanks for giving me the opportunity to share my work. So I'm doing my PhD in the supervision of Francesco Urbani, and the main question that is guiding our work is the question of how the brain learns. And of course, the brain is a very complex system. So to start, we focus on learning with simple, high-dimensional chaotic systems. So in fact, the simplest model you can make of the brain is a recurrent neural network. So we will consider neurons, which are encoded into this variable X. And the neurons are randomly connected with a coupling matrix J. And in these systems, the neurons are dynamical variables. So you can consider, for instance, the foundational model of Sampolinsky, Crisanti, and Somers, where the neurons have this kind of dynamics, where you have first a relaxation term, and then you have the interactions between all the neurons in the system. And these interactions are, again, random because of these random couplings. They are also non-reciprocal because the coupling matrix is asymmetric, and they are non-linear, in this specific case with an hyperbolic tangent. And what Sampolinsky, Crisanti, and Somers showed in this seminal paper is that if these random interactions are strong enough and the strength of the interactions is tuned by this parameter G, then the dynamics of the network can be chaotic, which is characterized by endogenous fluctuations in the dynamics of the neurons. And this arises specifically because we have high-dimensional, non-reciprocal, and nonlinear interactions. So during the talk, I will consider two models. The first is this model that was originally studied by Sampolinsky, Crisanti, and Somers. And I will also consider a new model that we introduced during the PhD, which is basically a more analytically tractable version of this other model. And the reason for this is because instead of having a hyperbolic tangent as a nonlinearity, we have polynomial nonlinearities, which of course are easier to deal with. But essentially, we've shown that the two models have the same phenomenology. So I don't want you necessarily to focus too much on the details of the models, but the key idea to remember is that we will always have these random recurrent interactions, which create chaotic activity in the system. And then we will add some extra terms to the dynamics to account for some learning paradigm. Okay, so let me start by giving you the big picture for the problem of learning in recurrent neural networks, because it's actually pretty different from traditional machine learning settings. So in machine learning, learning is essentially performing a high-dimensional fit between a high-dimensional input and a desired output. And in the simplest of settings, this fit is performed by a feed-forward neural network. And this feed-forward neural network is trained to minimize a cost function via gradient descent. But in the brain, and so also in recurrent neural networks, the learning rules are actually largely unknown. What is more likely is that learning would be an emergent property arising from local and asymmetric plasticity rules, rather than a gradient descent on a cost function. And this is because the dynamics of the neurons and the dynamics of the synapses that connects the neurons, in general, it will be some out of equilibrium dynamics. So to study learning in these systems, we really need to track the dynamics of the system. In fact, we need to track both the dynamics of the neuron and the dynamics of the synapses, which are coupled to the dynamics of the neuron and which evolve through some training algorithm, for instance. And we can do that using a technique from statistical physics called dynamical mean field theory. And because studying training dynamics is a hard problem, it can be useful to study simple models like the one that we introduced during the PhD. Okay, so now I would like to discuss two learning settings. The first one is called forced learning, and the second one will be about a generative model. So let me start with force. So with forced learning, the setting is the following. We have a recurrent neural network, which will act as a reservoir of dynamics. And from this recurrent neural network, we can define a readout neuron that I call Z, which is just a linear combination of all the neurons in the system. through some output weights WO. And the important point is that the activity of this readout neuron is also fed back into the system. So the loop is closed and the setting is fully recurrent. So before training, we are in a situation where the activity of the network is chaotic, and thus the readout neuron is doing some erratic trajectory. And the goal is that after training, dynamics lands on a limit cycle where the readout neuron is reproducing some target periodic function, f, and correspondingly, the dynamics of the neurons inside of the recurrent neural network will also be periodic. And we want to do this by training only the output weights WO. So it turns out that this task is not an easy task. In particular, gradient descent methods will be ineffective here because of feedback effects. So because the activity of the readout neuron is fed back into the network itself, you have a problem which is known as vanishing or diverging gradients. And so a celebrated solution to this problem was found in 2009 by Susilo and Abbott in this paper, and it's called the force training algorithm. So essentially, the algorithm works by enforcing that at every step of training, the readout neuron should be very close to the desired outputs. And this is already very different from standard gradient descent method, where you usually start with an error which is quite large, and you try to decrease the error as training progresses. Here, instead, the error will be very small from the start, and instead, what the algorithm will try to do is to... Yeah, is there a question? Okay. And instead, what the algorithm will try to do is to stabilize the corresponding attractor. Can you just tell me if everything is okay?
I think yes, okay. It's okay. Sorry. I heard also something before, but it was an error, I think. So okay, I think you can continue.
Okay, so yeah, the error will be always small during training, but what the algorithm will try to do is to stabilize the attractor. And the way it does that is by giving dynamics to these output weights. So the idea is that if at every step of training I can choose the value of these weights, then I can choose them in such a way that my readout neuron is very close to the target output. And then the algorithm will try to dampen the dynamics of these weights in order to stabilize the attractor. So that's the idea. At the time when we were studying force training had been shown to work empirically on the foundational model of Sampolinsky, Crisanti, and Sommers. So, of course, the first question was, can force also train our new dynamical systems? So these are results from finite size numerical simulations, just to show that force can also train our new simple model. So, for instance, if you look here, this is the dynamics of the readout neuron before training. So it's doing something that is chaotic. Then here training starts, and because of the algorithm, the readout neuron is forced to reproduce the target function. And correspondingly, there is initially a very big update in the weights, and then the weight updates are progressively dampened. And then this is after training. So the weights are fixed, and the readout neuron is autonomously reproducing the desired periodic function. And so the network was sufficiently trained. And in this way, we can learn a wide range of functions. So here I'm varying the amplitude of the functions, and here the frequency. So as I said, force had been shown to work only empirically at the time. And so a theory of force learning was lacking. So what we did is to study the force training algorithm with dynamical mean field theory. And now I will give a very brief crash course on dynamical mean field theory. So the idea is that you start with your finite size system, which is a high dimensional dynamical system with n coupled dynamical equations, where n is the number of neurons you have in the system. And dynamical mean field theory is exact in the infinite size limits. And so what happens when you take n, the number of neurons, n to infinity, what happens is that all the neurons in the system become equivalent to one another. And so what you end up with is an effective stochastic process for a single degree of freedom that I just call x. which is written here. And you can notice that the random recurrency interactions become a noise eta, which is a Gaussian noise. And the variance of this noise depends self-consistently on the activity of the neurons. And then from this effective stochastic process, you can derive what we call the dynamical mean field theory equations, which are flow equations for the relevant macroscopic observables of your system. And in this specific case, so these DMFT equations, they describe the dynamics of the neurons and also of the training algorithm. And they are exact in the infinite size limits. And in the case of the simple model that we introduced, these DMFT equations are closed. And so you can easily integrate them numerically, and you have in this way access to training dynamics. So this is the results that you get from integrating these DMFT equations. So in the top panel, I'm showing the activity of the readout neuron, and I'm comparing it to the target output, so the function that we want to learn. So training starts here at t equals 0, and because of the algorithm, the readout neuron is forced to be very close to the desired outputs. And then at t equals 50, we stop training. And here we see that the readout neuron stays very close to the desired outputs. So the system was sufficiently trained. And this is already a non-trivial result because it means that the force algorithm is also effective in the infinite size limits. And what's also interesting is if you look at more closely at the error, so the difference between the readout neuron and the desired outputs, you see that first of all, the error is very small. And what's interesting is that after you stop training, you see that the error slowly increases. So actually the attractor you learn, so you land upon after training, is not completely stable. So the dynamics moves slightly away from it. And of course, this attractor will be the more stable the longer you train the system. So in particular, if I train the system for less time, so if I stop training at t equal 25 here, then you see that the dynamics after training moves significantly away from the desired attractor. And the error is much bigger. And I think it's still an open question whether the dynamics would land on a nearby attractor, which is not exactly the target one, but not too far either, or whether it would actually keep drifting away and maybe again become chaotic or even diverge. Okay. And so lastly, I would like to talk about a generative model, where the idea is to use the internal high-dimensional chaotic activity of this system as a sampling noise for training. So now I will consider a network which has a two-layer architecture. So we have one layer of neurons that are called V for visible neurons, and another layer which is called H for hidden neurons. And in this specific case, the architecture is called restricted because we only have connections between the two layers. But it's still a recurrent neural network because you have connections that go both ways instead of a feed-forward neural network where you will have only connections going one way. And the idea is always the same. So both the visible and hidden neurons have some dynamics, and you have some random interactions that arise because we have a backbone of random connectivity. And these random interactions, they create chaotic activity in the system. And then on top of that, we have some learning that is happening. So in particular, we add some connection matrix A and some fields B and C, which act on the visible and hidden layers. And these A, B, and C are trainable parameters. So the task is a generative modeling task. So you have a data set with data points xi, and the goal is to generate new samples which correspond to the activity of the visible neurons at a special sampling time big T. And the goal is that these generated samples should be statistically similar to the data sets. So the goal is not exactly to memorize the data sets, but rather to learn the statistics of it and to be able to generate new samples that look like the ones of the data sets. And so to do this, we use a contrastive Hebbian learning rule. so at every epoch of training alpha, the parameters are updated in this way. And the idea of the learning rule is to compare two states. So a clamped state where the activity of the visible neurons are clamped to a data point, meaning that I can run the dynamics of my network while the visible neurons are equal to a data point. It's as if the network was seeing an image, for instance. So these are averages over a subset of my data set. And then these negative terms, they are also averages over samples, but this time samples coming from the free dynamics of my system, where the dynamics can evolve freely. So,
Samantha, excuse me, can you tell me what are the chi's exactly?
Yes, thanks for the question. So the xi's are the data points, and the chi are the activity of the hidden neurons, while the visible neurons are clamped to the data points. So yeah,
Thank you.
This represents the clamped states. And instead, V and H are the dynamics of the free neurons. So the pipeline is represented here. So at every epoch of training alpha, we want to update the parameters. And to do that, we need to generate these samples. So we do some parallel sampling. So running the dynamics of the network in parallel, starting from different initial conditions. And we run the dynamics up until the sampling time big T. At time big T, we save all the configurations, and we use them to compute these averages and update the parameters. So if you're familiar with the Boltzmann machines, you might have noticed that this setting is very similar to the one of restricted Boltzmann machines. Indeed, the key difference is maybe that we start with a backbone of connectivity, which is random and asymmetric. And that creates chaotic activity in the dynamics of the neurons. And the idea is to try to use this chaotic activity as a sampling noise. So initially, before training, the dynamics of a network will be chaotic, so looking something like that. And then as training progresses, learning should suppress chaos, reduce it. And the goal is that the training dynamics would reduce the level of chaos just enough to try to reproduce the statistics of the datasets. So that was the idea. What we did is a kind of a numerical experiment to see what would happen. So we trained the system on two very simple datasets, which are MNIST and fashion MNISTs. And these are snapshots of the dynamics after training. So in these plots, each row is a run of the dynamics, and each pixel is the activity of one visible neuron. So at time t equals 0, you initialize the neuron randomly. And in fact, this random initialization is the only source of noise in the system. And so for a given random initial condition, you see that you end up in a given fixed point. So in this specific case, the chaotic dynamics was completely suppressed by training because you end up in fixed points all the time. And these fixed points, they look very much like samples coming from the training data sets. And what's maybe more interesting is that if you look at the samples that were generated at the sampling time big T, so corresponding to this column here and this column here, what you can see is that the dynamics has not quite yet reached the fixed points. The samples are a bit more noisy, but also a bit more diverse, which maybe is better for a generative model. And you can also see a phenomenon known as mode collapse. So for instance, if you look at this row, you see that at the sampling time big T, so here, the network is generating something that we would classify as an 8, and then it later evolves to become a 5. So it gets attracted towards another attractor. So you can also assess the performances of the network in a more quantitative manner by defining some error function that assess the quality of the generated samples. So I won't go into the details of these errors, but so here I'm just plotting them as a function of the time of the dynamics of the neurons for different training epochs. And what you can see that these errors, they have a minimum, and they have a minimum at specifically the sampling time big T, which is the time that we use to generate samples during training. And this is a bit what we saw earlier, is that even though the samples at time big T were a bit more noisy, they were also more diverse, and that's maybe better for generative performances. And overall, both in the shape of these error function and in their numerical value, they are very similar to what was obtained in this paper by Dessel and collaborators, where they trained restricted Boltzmann machines also in an out-of-equilibrium fashion. So yeah, this was just a proof of concept to see what would happen for this simple out-of-equilibrium contrastive Hebbian algorithm. And lastly, the last thing I want to show you is the receptive fields, which are of interest to the neuroscience community. So the receptive fields are the weights that connect one hidden neuron to the visible layer. So here, each image is the receptive field of one hidden neuron. And before training, we have a random initialization of the weights, so the receptive fields are also random. And after training, we see some emergence of some spatial structure for roughly half of the hidden neurons. And this is also something that people see with the restricted Boltzmann machine. So in conclusion, I talked about a simple model for recurrent neural networks that we introduced during the PhD. It's simple because it has a polynomial nonlinearity, which makes it easier to study through dynamical mean-field theory. And I didn't really show you this, but we really think it's a good model to study because it has the same phenomenology as more standard models. And it can be useful to study plasticity and training algorithms. And in particular, I discussed two training algorithms, which are forced learning and this generative model. And in both of these settings, we can study the training algorithm within dynamical mean-field theory. So thank you very much for your attention, and I'd be happy to answer if you have questions.
Okay, thank you very much, Samantha. Today, the task of the chairman is made simple because usually one has to shorten the seminars. Today we are in advance, but better, so we have more time for questions. I heard something. Yes, Luca.
Okay, maybe it's too technical, but I was wondering, how do you solve the MFT equations, and how can you be more specific on how it is the procedure doing the dynamics and the learning?
You mean how did we end up with these equations?
Oh no! Once you have then okay, I trust you blindly. Okay, so how do you solve them? And then you said also that in the polynomial model you use, they are closed equations, are they? So if you can tell us something more.
Okay, yeah, so in this case, we just solve them numerically. So you can discretize them, for instance, using a Euler discretization, and just integrate them in your computer because they have a causal structure. So the integration part is rather easy to do, but you have limitations because of memory effects. So in particular, you see that in these equations you have a 3 tensor, and you have to keep in store the dynamics of this 3 tensor, and so you're limited in the amount of time step that you can integrate the dynamics for. So for instance, in the results, I did the integration up to 150 times. Up to t equal 150. That was rather easy, but I couldn't do much for much longer. So that's one limitation. And yet the simplification of the simple model is because if you look at the effective process, so the variance of this noise eta, it depends directly on the correlation function of the neurons, so the variables x. And for other models, for instance, with the model of Somponiski, Kitsanti, and Somers, that's not the case. And that means that the MFT equations are not closed, and you're kind of stuck at the level of this effective stochastic process.
Okay, thank you. But is the fact that you cannot integrate it for very long times, is it a drawback for learning, or you don't need to run your dynamics too long? I mean, for specifically, I mean, for the purpose of the learning you have to do. So I just asking.
Yeah. So it means, like you said, that you can't integrate the dynamics for too long. So maybe you can't describe this type of learning exactly, but if you're interested in more qualitative understanding, then I think it seems to be enough to get some understanding.
Okay, thank you.
Okay, thank you. We have another question from Carmel.
Yeah, thank you. Actually, when looking at when you were presenting, I saw you mentioned the fact you like learning overlearning. I want to know if there is the possibility of having overlearning in this, because I know usually in these cases we can have some types of overlearning, like it overlearns, so it learns so much so that it becomes like somehow mad. Is that possible in the system?
So that would be, for instance, if you keep on training this system. So you see, for instance, here so I didn't say, but yeah, these are the behavior of the weights during training. And maybe if you keep on training, you see that some weights could maybe become very big, and then you would have numerical instabilities. And I guess that would be an instance of overlearning.
Okay.
And I don't know if you could do some kind of regularization to stop that, but yeah, in practice we just do some early stopping, like when the network is behaving well, we just stop training. And in the case of the generative model, so in this case we didn't do any regularization of the weight, so I guess that could happen too. But in practice with Boltzmann machines, they add some regularization of the weights to avoid that also. But yeah, in general, if you don't control, if you don't control for that, that could happen.
Okay. The second question I had, thank you very much for the first one. The second actually is if between the two, between the generative modeling you use and the forced learning, which one is like your preferred one?
I like them both, honestly. Maybe let me say that in general, we are interested in training algorithms that are also biologically plausible. And actually the force algorithm, this version of the force algorithm is not biologically plausible. Whereas what I really like about this model is that it's very simple. So the learning rule is local and actually Hebbian, which is interesting for applications in neuroscience. And it's just, everything depends on the dynamics of the network. It's very simple. But yeah, thanks for the question.
Okay, now we have a question from Lorenzo.
Yes, thank you. Hi, Samantha. Thanks a lot for the talk. That's really interesting. I have a question on this part on generative modeling. Please tell me if I say something really like stupid or off. But is it right to interpret these factors G and K that you have in the respectively as prefactors in the random and learnable parts as kind of the temperature in Boltzmann machines? Because this looks like this is very similar to a restricted Boltzmann machine, just in continuous time and with like random interactions instead of fixed one. And it looks like if you just use the learnable part, you have some deterministic sampling with no generation, and if you just use the random part, you just get gibberish, and so you can kind of tune them as a temperature. That brings me to the second question, which is more of a comment, I don't know, which is if that is true, your generated images look really sharp to be generated by a restricted Boltzmann machine. Like I would like they're really great. Okay, so do you have any insight why this kind of continuous time model or what tricks make this much better of an equivalent restricted Boltzmann machine?
Okay, so I didn't know the samples were better than restricted Boltzmann machines.
At least from my experience, I might be like bad at training restricted Boltzmann machines, but
okay, I don't know. So to go back to your first question, so yeah, you're right in the sense that, for instance, this parameter G, it tunes the strengths of the random connections, and so the bigger G, the more chaotic activity you have, at least in the beginning. and this K here, it's actually the learning rate. So yeah, by increasing G, you can control the level of chaos, and there is a competition between this term, which creates chaotic activity, and this term, which essentially suppresses it because of learning. In this specific case, so when we trained on MNIST and fashion MNIST, what we actually see is that very quickly during training, chaotic activity is suppressed, and that's because these terms become very strong and they quickly overpower this. So yeah, I'm not sure if it how we could relate it to a temperature, let's say. But related to the comments that you said that the images were sharp. So I also did a test to try the system, to train the system without these terms, so putting G to 0. And what I see is that I get samples which are also kind of good looking, but they are less sharp. So the images are a bit more blurry. And I don't know, now that you mention it, maybe that would be closer to what people see in restricted pulse machines. But yeah, I wouldn't know.
Thanks. That's a nice thing to know. Thank you.
Okay, question from Gianluca. Gianluca Peri, I don't hear you. Your hand is raised. Okay, let's move to Lucilla, then we'll come back to Gianluca.
Okay, thank you, Samantha, for the very nice talk. Just a curiosity, in your model, the first and the second layer have a connectivity all to all. I was wondering, the results you find are affected by the structure of the connectivity if you have a sparse network instead?
I didn't try. My guess would be not, but I didn't try.
Okay.
So yeah, I don't know. Maybe what I can say is that what I did try to do is after training, so you see in these receptive fields, so in these connections, you have connections that are very large and connections that are very small. And so just for fun, I tried to cut out the very small connections and see if only the strong connections mattered. But actually, if I did this cutoff, then the samples that were generated were not as good. So in a way, all the connections mattered, but that's also because the system was trained in this way. If you train the system with a sparse connectivity from the start, then I don't know what would happen.
Okay, this is an interesting point. Thank you.
Sorry, can you hear me now?
Gianluca, sì.
Yes, thank you. So I just wanted to ask a really basic question. I wanted to know more about the nonlinearity, because like you told us that we have a polynomial nonlinearity instead of hyperbolic tangent, and I didn't quite get how it works in the network. So that, thank you.
So I didn't want to get into the details of the models, but yeah, so in this model you have pairwise interactions with a hyperbolic tangent as a nonlinearity, which means that each neuron receives an input, which is this sum, and so it has the contribution from the nearby neurons in the network is goes through this nonlinearity, which is saturating. And in our new model, instead of having this hyperbolic tangent, we have the simplest nonlinearity you can take, which is quadratic. And in particular, so that means you have still these two body parts, but now with just j times x, but we have also j times x squared. And in general, we also added some 3-body interactions, which are maybe a bit more abstract, but that's the most general situation you can consider. Is that clearer?
Yeah. Thank you so much.
And yeah, maybe just the caveat is that if you do this, then since the nonlinearity is not saturating, you can have dynamics that diverge. So you need to modify a bit the relaxation part of the dynamics by adding some confining term here, which, yeah.
I have a curiosity, since I don't see any other questions from the audience. So you show that in the generative model, if you stop the procedure at the intermediate times, you get something which is very different from the original. Do you have the feeling, I know that you cannot go to infinite times because of the restriction that you mentioned, but do you have the feeling that in going to infinity with time, you maybe are just memorizing instead of generating, or you know something about that?
Yeah, so maybe just a specification. This is not the time of the training dynamics. This is after training, just looking at the neuronal dynamics. Mm. And the point is, when we did the training, the network always the network never saw what happens after this sampling time big T. So we always generated samples using this time big T. Of course, you could take a big T larger, so going into this steady state here, but that can be a bit heavy when doing numerical simulations. And yes, indeed. So these samples here, they look very much like samples that were from the training data points. I don't think they are exactly the same, but since these data sets are very simple, it's hard to know if they're exactly memories or not. Yeah, so that's, I don't have I didn't explore that very thoroughly, let's say. But yeah, that could be the case, that the network learns some kind of deep memories, which are small with respect to the whole breadth of the data sets. But what happens is that before reaching these attractors, you have transient attractors, which are a bit more diverse, and that would explain, for instance, this mode collapse. And yeah, and that could be why the performances are better at the sampling time big T rather than at long times.
Okay, thank you. Any other questions? I don't see any. So before thanking the speakers again, let me remind you that next Young seminar will be in April, on the 9th of April. And I think we are done. Thanks to the speaker again. Thanks to everyone for being here. And let's meet again.
Thank you all.